Okay, so sorry, just finished some nice cheese and crackers. So we've been looking this week in model selection. So what I'm going to do is we're going to go across to our studio and we're going to have a case study where we're going to do some simple model selection to sort of illustrate some of the various methods. The question I always get from students is, which is the right method? It depends is probably the best answer. Learn them all, be proficient, be able to bounce between them. Now the classic things, I've said this before, model early, model often. All models are right, just some are useful. So please don't feel there's an answer, there's answers, and we sort of, explore them. So here's the data. We're going to look at the MPG data set. So let's load some packages. Sorry, bit of cheese in my back tooth. That's obviously taking longer than I wanted. Now, MPG data. So the whole idea of this is they took a load of cars and they're trying to look at fuel efficiency. We've got city fuel efficiency, CTY, and the highway fuel efficiency. And that's what we're going to do. We want to be able to predict this. Work out what our best predictors are for this model. So let's start with some cleaning. I'm going to get rid of the highway. I'm going to focus on city because that's generally what I do. So we'll clean up and get rid of highway. So I've taken my MPG data and got rid of the column highway, which is HWY. So this column's gone. So now we're going to do what we call feature engineering. So features is the data science machine learning term for predictors. And what we're going to do is for each of our predictors, we're going to do a bit of cleaning. We're going to think about what we can do. So let's start with manufacturer, this first column. And what we see here is we've got a lot of different manufacturers. And the problem is some have very few cars in the system, for example, the Lincoln. So I'm worried that you're not going to get good representative data. So what I'm going to do is I'm going to lump these together. I'm going to say when I get something like Dodge and I got 37, that's fine. But when I have something as small as, for example, Lincoln, there's not many. So I'm going to reduce that down. So I'm going to use from the factor package the thing called factor lump min. Basically says, if you have 10 or more, leave you as is. If not, I'm going to lump you all together into a new level called other. So let's run this and run it again. And you can see now they're all 10 or more. And we've got this whole thing called other, which has 33. So Lincoln's disappeared. It's now called other. So it's a quick way of lumping things together. So we've got our MPG. What's the next thing we can look at is model. So let's do a similar thing with model. Let's have a look at model. And the problem with model is we have a lot of different stuff. It's a bit, within each particular thing we have a different model. It's not a good predictor if you think about it. It's too car specific. So in this case, to make it easier for myself, I'm just going to remove that. So we get rid of model. Displacement is just a number. I'm not too worried. I can leave that as. I don't need to clean it. We could do some EDA on that, but that's fine. Year's the same, sun's the same, but transmission. Let's have a look at transmission. So if we look at transmission, we have lots of different forms. But again, how can I simplify this? In this case, I only really care, does automatic versus manual make a difference? So let's do that. What we're going to do is we're going to convert trans. So we're using mutate. I'm going to use an if-else. An if-else is saying, if when you look at it, it has auto in it, call it auto. If not, manual. So that's what we're going to do. We're just cleaning up. So now I've just got auto or manual. And there's lots, I've got 77 and 157. That's looking good. What does drive look like? I'm pretty happy with that. Only 25 for rear wheel drive. I'm not too worried. Let's look at fuel efficiency. Again, sorry, not fuel efficiency, fuel type. There's a couple here that are a bit small. I want to lump these together. You could reclassify and say, let's call C, D, and E, but I'm just going to use my lump command. Looking pretty good. What about class? Not bad. You got this two-seater of only 5. You could try and merge that into one of the others, maybe with minivan, but I'm going to leave it. Finally, we know that our linear model will take all our characters. So if we look at our MPG, you've got a factor here, you've got a factor, we've got a character, a character, a character. I want to make sure they're all factors. So here's my command. I'm going to say use mutate across where everything, so it's basically looking for any column that is a character, convert it to a factor. So let's do that. And now when we have a look, it's looking pretty good. We've got I was about to point to the screen then. I was going to say, and there's a factor. No, what we've got, I'll use my cursor. This is a factor, this is a factor, 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 factor. All good. So that's your cleaning data. And I mean, in this case, I've already looked at this data, I knew what I was going to do, but what I sometimes do is I will go and do my EDA, exploratory data analysis, and then come back and do my cleaning. And I have this iteration process of flicking between them. And also, I've got to the point that I've been modeling and then doing assumption checking and go, oh no, and go back and do what we call feature engineering. So don't believe it's a linear process. The final story you tell, like in this case, is a linear process. But when I'm doing it, I'm always sort of going back and updating. Let's have a quick look at our skimmer. So we've got our factors here, we've got our different sorts, there's no missing data, no missing data. It's a pretty good data set, it's pretty clean already. We've got 234 types of car, we've got n columns, we've got 5 are factors and 4 are numerics. So now in my EDA, the next thing I do is I will explore my data. And the two things we've been looking at is the first thing, I'm going to look at some sort of visual representation of my response variable. In this case, it's a quantitative variable, so I'm going to do a histogram. And what we see here is it's a little bit right skewed in the fuel efficiency, the city fuel efficiency. I think it's unimodal. There's a lot of data missing here. It's not particularly clean, but not too bad. I'm not overly worried about doing any major transformations, but we know we can do that with box Cox. So what I'm going to do here is I'm going to grab all the numerical predictors and I'm going to basically do a scatter plot. So this has grabbed all the numerical predictors, so we do a scatter plot. So whenever I'm comparing, in this case, a response variable that's a number, a quantitative variable, and I have a predictor that's a number, I do scatter plot is the go-to. So we can see as the number of cylinders increase, my fuel efficiency goes down. As the displacement of the car increases, my fuel efficiency goes down. And finally, there's not a lot of difference there, is there? You can't see a major effect between our 2 years that we have in this data set. And I want to do the equivalent for my categorical predictors, my factor predictors. In this case, we're going to do a side-by-side box plot. So here we've got it. You can see that, for example, drive seems to make a big difference. Front and rear is much more efficient than fore and rear. Not a lot of difference between the fuel type. The manual seems to be more efficient than the automatic. Manufacturing, not a lot of difference. And class, not a lot of difference. I'm also going to look at the correlation between my predictors and my response variable. So I'm using here what we call a correlation plot. So basically, this looks at the correlation between displacement, year. The color tells me whether it's a positive linear relationship or a negative. So for example, displacement and the fuel efficiency is negatively correlated, and the size of the circle tells us how strong. So along this, you expect to have a big blue circle because they're all correlation of 1 between themselves. What do we see? Cylinders is negative correlated with fuel efficiency. The same displacement is negative correlated with fuel efficiency. And that's about it at this point. So let's think about our various methods. The first thing we looked at is the backwards p-value method. So what do we do with that? We're going to fit the full model. So here's the full model. I fit it and have a look at it. And the rule is as simple as this. I look at this and I look at all my values and I look at the p-values. Now the problem we have here is, for example, manufacturer has numerous coefficients because it's a numerous levels because it's a categorical. So the easy way to sort of make decisions about whether a manufacturer should be in or not is to reduce this down to an overall test or an ANOVA. So I'm going to run my ANOVA. And what we're doing here is you've got each of my predictors. And the main thing we're interested in is we go over and we look at the p-value. And the first thing we do is we say, are all the p-values less than 0.05? If they are, we can stop. They all need to be in the model. If there's any p-value that is greater than 0.05, in this case, fuel efficiency, what we do is we find the one that's largest out of all of the ones that are greater. So there's only one, so this is the largest. You then remove it and update your model. So that's what I'm going to do. I'm going to take my model, I'm going to update it, I'm going to keep, the dot says keep the same response variable, keep all the same predictors, but remove fuel type. So now again, we have a look. We look at this, we say, are all the p-values less than 0.05? Yes, stop. So that's the backwards. You look at it and you go, are any p-values greater than 0.05? Yes. Find the largest, remove it, go to the next step. And keep doing that until they're all the less than 0.05. So that's backwards using p-values. You could also do it, forwards and step using p-value, but it's really long because you're doing it by hand. And it's often a lot easier to use AIC. So remember, AIC is this Kaike's information criterion. It has a measure of your likelihood, and it also has a penalty for the number of turns, and the smaller, the better. So what we're going to do backwards. So we're going to basically say, take your full model, try taking out every single predictor, see what the AIC is. If there's one that drops it a lot, choose that one, keep going. So we're just seeing if we can remove a predictor step by step. But we don't have to do this. The reason it's so good, we don't have to do this by hand. There's a step function built in to the stats package. So I give it the full model and I just run it. And off it goes, and it tries removing all of them. It looks at the AIC, it has a look at it, and says the AIC when I don't remove anything is 328.65. Here's the AICs if I remove stuff. They're all bigger, so it's basically saying don't remove anything. So that's your summary back. All good. We could do forwards. So now I'm going to start with the smallest model I could have, which is the null. So I've just got an intercept. And then what I'm doing is I'm going to say, well, here I have to give it scope. I have to say what's the biggest model. Because in the first one, we knew the biggest model because we'd given it. But here it doesn't know. So we say, this is the biggest model I want you to consider. And it's going to start adding stuff bit by bit. So let's break it down. We have to go all the way back here. It started with the first null model. And then it said, right, if I add cylinder, this is my AC. If I have displacement, here's my AIC. If I have class, here's my AC. It tries adding each one. It says, which one gives me the smallest AIC? It's the one with cylinder. So now my model just has cylinder. So now I try adding in class, drive, manufacturer, etc. And it says, which gives me the smallest AIC? The one where I have cylinder plus class at 366. So now I've got cylinder plus class. Now it tries adding everything in. Drive. Now it counts trying anything in, manufacturer. And it keeps going until we get eventually, this is my best final model with an AIC of 328. Finally, we've got backwards, we've got forwards, we could do both. So I give it the null model, I give it my scope, I now say both as opposed to forward, and I run this. And again, it does all these steps, and it's basically taking steps backwards and forwards until it gets to the final model. I'm going to compare these models. I'm going to do what we call Stargazer. And that gives me something horrendous because it's designed to give me HTML. So what I'll do is I'll quickly wait a second and we'll run this in HTML so we can see what that actually is producing. It will also produce LaTeX if you want to use LaTeX. It will also produce text, but when I looked at the text, it was a bit over the screen. So let's just take a while because this is just doing lots and lots of model fitting. So now here's my output, and let's go back to where that Stargazer is. So if we come down all the way here, there's lots of stuff in my report. There we are. So Stargazer is really nice. Here's my 4 models I have. Here was my backwards p-value. Here was my backwards AIC, my forwards AIC, and my both. And you can see that basically all these models are the same. They've got the same coefficients. Here's our standard error. Indicates the p-value. Except the only difference is when we did the p-value, we didn't have fuel type. Well, in the AICs, we do. So to some extent, we've ended up with 2 possible models. We've got one which has everything and fuel type, and one that doesn't have fuel type. So how can we decide between them? Now, it might be that you just have a favorite. You always use AIC, you'd go for the AIC model. You always do. But what I'm going to do here is I'm going to use this to illustrate our 5-fold cross-validation. So remember what I'm going to do is I'm going to take my data set, and I'm going to split it into 5 parts. And then I'll take one part aside. I'll take the other 4 parts. I'll train that. I'll fit my model to that for my 2 models. And then I use my fitted model to predict for the test and see how good it is. And then I go to the next piece. So I'm always using 4 pieces to predict the 5th. So first of all, if we look at it, we can't split into 5 equally. We're going to have, most of them are going to be 46 and some are going to be 47. So the way I'm going to do it is I'm going to basically give each row a number, 1 to 5, randomly. And I'm going to do that so we have our repetition and we've got our folds. So our folds, all I've done here is I've given the number, so I've got 1 47 times. And then 2 47 times, and then 3 47. Now that's going to give me too many numbers. So what I'm going to do is I'm just going to cut that down. So basically the 5s don't get as many. And then what I'm going to do is I'm going to take this and I'm going to permute the order. So if I run this and have a look, so what it's done is it's randomly, so altogether approximately, well, I can tell you exactly how many. 47 of those rows have the number 1 next to them. So they're going to be in fold 1. 47 will have 2, 47 will have 3, etc. And this is randomly allocated. 5 only has 46, but they're pretty balanced. You couldn't divide the number of rows by 5. So what we've done is basically we've randomly put each car into a fold. So now what I'm going to do is I'm going to calculate the root mean squared for M1 and the root mean squared for M2. So that's model 1 and model 2. So all I'm doing here is I'm creating vectors that are, to show you, just empty. They're just zeros in there, ready to take my numbers. So what I'm going to do is I'm going to go, for each fold, what I'm going to do is I'm going to grab my train data, which is all the folds not equal to. So if you go to the first one, and it will grab every observation that's either a 2, 3, 4, or 5, grab them aside, call that train, and the rest, the ones that have fold 1, are my test. And I will do this 5 times. So I'm splitting my data into my train data and my test data. Then what I do is I take model 1 and I fit it to the train. So here's my model with the fuel efficiency. Here's model 2 without the fuel efficiency. Then what I do is I go predict using model 1 for my test data and predict using model 2 for my test data. And then I work out the root mean square. So what's the root mean square? I take the observed CTY minus what I predicted with model 1. I square them, I take the mean, I take the square root. In here, I've taken the observed CTY minus what I predicted with model 2. I square it, I take the mean, I take the square root. So that does for all of them, like that. And then, now I'm just taking the mean. I should have been more accurate. I should have adjusted and taken each root mean square error, square it, times it by the n, do it that way. But I'm just doing a comparison. I'm just going to take the mean of each one. And what I want is I want the one that's the smallest. And you can see that model 2 is on average give me the smaller root mean square error. So that means I should take model 2. So now I've decided model 2. Let's go and fit it to all the data so we get better estimates. And let's have a look at what this actual final model does. Well, first of all, we could have a quick look at the assumption plots. Now we've got to this point. You can see it's not too bad. I get some discretization. You can see these sort of lines and I think I'm getting a little bit of heteroskedasticity. Notice this blue line is increasing towards the end. So again, not a bad model, but I could definitely improve it. You also see some non-normality here and here. So again, I might want to go and improve my model, but I think this is a pretty good start. So we're going to stick with this model. This is a model we decided is the best. We also want to see what that description is. You could look at your summary and go, well, what's the summary of my final model? But that is hard to interpret. That is a hard thing to interpret. So instead, I'm going to go and use a package we've not seen before called the GG effects. And what you do, unload it, is first of all, let's see what it does. So just wait a second. It's doing what we call marginal prediction. So let me explain what this is actually doing. Let's go all the way back. So the first thing is it looks at manufacturer. And it says, what I'm going to do is I'm going to set every other predictor other than manufacturer to the average. So for example, it set displacement to the average of all the displacements in all the data, which is 3.47. For year, it set it to 2003.5 and cylinders, etc. Now, how does it do the average for categorical variables? It sets it to the mode, the most common, the highest frequency. So it's set, basically in the model, all the other predictors to the average, and then for each individual manufacturer, it gets the predicted value with confidence intervals. Okay. Here's displacement. With displacement's a quantitative variable. So it set everything. So manufacturer set to Audi, that's the most common. Years set to 2003, that's all good. But what it does with displacement is it's taken the minimum and the maximum and it's split it into a nice range and given us predicted values. So first of all, you get these nice little tables that give us predicted, what we call marginal predicted, and 95% confidence intervals. But the nice thing is we can convert that into a whole load of plots. So it's now going to sit and it's going to do a load of plots. And now we can go back through these plots. You could plot one at a time if you wanted to. And it will show you the effect of that variable. So there we've got here. So what do we see here? We see that all the fuel efficiencies are pretty regular, but the predictive model says that high and I is a lot worse for fuel efficiency. What do we see here? We see that if we set everything to the average and we increase displacement, as displacement increases, we see that the fuel efficiency decreases. What about this one? As our years increase, we find that our fuel efficiency increases. As our number of cylinders increases, our fuel efficiency decreases. There's not a lot of difference between trans. I mean, it was in there in the moment because it improved the AIC, but not a lot. Manual slightly better. With the drive, yes, front wheel drive is better. These are all agreeing our predicted model with what we observed in the data. And with our fuels, we get the other is a lot better than the R and P, which I cannot remember what they are. I think it's petrol and something else. And then finally, for our type of class, the fuel efficiency for the two-seater is much better than all the rest. The worst is your minivan. You know, it's a large, big thing. That doesn't surprise me. So there's all our plots as well. So there we are. We've got lots of different ways of fitting the model. Then once we've got a final model, we had a good look at the assumptions. We checked it. We know we can improve it, but that's all right. And we also looked at the relationships in that model. So there you are. That's all bringing all together this whole week of model selection. Cool. See you next time.